So, welcome everyone. It's great to see you again for another international webinar of RAS. My name is Nikola Bešinović from Delft University of Technology. I'll be hosting this meeting today. So we have a great honor to have Clark Cheng from NS talking about managing railroad assets and capacity for sustainable growth. Before that, we'll hear from one of our sponsors, Sam from Tiger Analytics. And I'll like to ask you first, you could turn off the microphones during the presentations. We'll have plenty of time for Q&A at the end of the talk. As you can see in the outline for today. So after Clark's talk, we'll have the floor open for questions. During the presentation, feel free to put questions for the speaker in chat. So then we can draw them afterwards and discuss after the presentation. So I would give floor to Sam.
Thank you, Nicola. I'm just sharing my screen.
Yes, please.
Great. Good morning, good afternoon, good evening, everyone. This is Sam Ramachandran from Tiger Analytics. I'm the Chief Sales and Revenue Officer, and I'm represented by my executive team here, our CEO Mahesh and our lead client partner, Setu. Before I introduce our lead speaker, Clark Cheng from Norfolk Southern, just a quick introduction of Tiger Analytics. We are a data science and advanced analytics consulting firm, professional services, with deep expertise serving railroad, transportation, and logistics clients. A team of about 700 odd data scientists and ML engineers globally. If someone can go on, everyone can go on mute, that'll be great. Thank you, folks. We have long and deep expertise serving the railroad, transportation, and logistics industries, which forms almost about a quarter of our business. We are a data science consulting service firm, very highly regarded by Forrester, highly rated by data scientists, known in the industry as a destination for data scientists. That's who we are. In terms of what we do, about 70% of the work we do tends to be in advanced analytics, machine learning, and data science, building predictive models to solve various business problems, which I'll talk a little bit about in a few seconds. We also have deep expertise in building the foundational data environments that serve analytics and data science for business insights, analytical data lakes, data marts. And once a predictive model is built, we also have the expertise to implement, operationalize, and scale some of those predictive solutions in your front-end environments. Think of the data sciences, data and engineering, ML engineering services organization that can be a potential lever available to you as you look to delivering data-led, analytics-led value to your internal clients and business partners. We serve almost 11 clients today in the railroad, transportation, and logistics industries. That includes some of the large railroads, rail car manufacturers, third-party logistics companies, trucking manufacturers, intermodal organizations, etc. Broadly, our expertise spans across supporting the sales and marketing function, supporting the transportation and network planning function, execution and operations, as well as classic fleet and asset management. This is just a quick summary of our expertise serving the transportation, railroad, and logistics industries. I'll be happy to chat with any of you if you have any further questions about what we can possibly do to help you and your analytics journey. With that said, it is my pleasure to introduce our lead speaker for this webinar ahead, Clark Cheng of Norfolk Southern. I would like to hand off to him. Thank you, Nicola.
Great. Thanks a lot, Sam. Clark is preparing his presentation. Let me give a few words. Clark Cheng is a RAS distinguished member. He joined the Norfolk Southern already in 1995, and there he leads the operations research group. His team develops decision support tools and provides analytical services to business partners. So they basically cover network optimization, operations planning, train scheduling, capacity planning, and I believe we'll hear about some of the great work at Norfolk Southern now. And yes, please enjoy the talk, and all the questions, please keep to chat, and we'll discuss them afterwards. Thank you very much. Please, Clark.
Hey, Nikolai, thanks for the introduction. Can you hear me okay?
Yes.
Okay, how about, can you see the slides on the screen?
Not yet.
Okay. Share the screen here.
Yes, it's coming.
Okay. Give me a second here. Okay, can you see my screen now? Great. Well, first, good morning, good afternoon, good evening, depending where you are. The title of my presentation is Managing Assets and Capacity for Sustainable Growth, how Norfolk Southern leverages operation research. Given the diversity of the audience, I'll start with an introduction of rail industry and Norfolk Southern, then talk about the OR tool suite and Norfolk Southern. In the following two sections, I'll talk about how we use OR tools to develop operating plan and manage assets and the capacity. Finally, wrapping up my talk with a summary.
I'm sorry, Clark. Apparently there is some low volume, so if you could just speak a little louder, that would be great.
Okay. Can you hear me okay now?
I believe it's better.
Okay, I don't have a place to really adjust the volume here, so okay, I can talk a little bit louder.
Perfect.
So the US has the largest free railroad network in the world. There are more than 500 railroads, but only a handful of large railroads. Norfolk Southern and CSX in the east, UP and BNSF in the west. Railroads carry the things we depend on, from consumer products, food, paper, lumber, farm products, chemicals, construction, finished vehicle, coal, and so on. There will be a strong demand for railroad service in the future. According to Federal Highway Administration, the freight shipments will increase by 62% from 2011 to 2040. Railroads are cost-effective, energy efficient, environmentally friendly, and safer. Therefore, railroads are the best way to take on the growing demand. But the railroads have to have the following: efficient operations, adequate assets and capacity, which means right assets and capacity in the right place at the right time. Last but not least, good customer service. Norfolk Southern has about 25,000 employees, operates about 20,000 route miles in 22 states and Washington, D.C. NS owned more than 3,000 locomotives. Actually, this number is from 2019. The actual number today is much lower after we implemented PSR. And 50,000 rail cars. Here are the 2019 financial highlights. The pie chart to the right shows a breakdown of 2019 revenue sources. Intermodal is the biggest contributor, followed by chemical, coal, agricultural products, metals, construction, automotive, and finally forest and consumer products. So why railroad need operation research? Railroad assets and capacity are not only expensive to own and maintain, but also need a long lead time. Take a locomotive engineer as an example. It takes up to 2 years to hire an engineer, starting with the hiring process, which takes a few months. Next, it takes about 6 months for a new hire to qualify as a conductor. Then it takes additional 12 months for a conductor to qualify as an engineer. That's about total 2 years. It takes even longer to build the infrastructure. Another example, in the early 1990s, Norfolk Southern intermodal business was growing in the Atlanta area. However, there was no room for expansion. Norfolk Southern identified an 800-acre site located about 14 miles from the Atlanta terminal, the place called Austell, Georgia. They identified this new location for a new intermodal terminal. Norfolk Southern purchased the land in 1993, but didn't open the terminal until 8 years later, which was 2001. So you can see the big span to do anything in infrastructure. In order to build capacity or acquire assets, we need to plan ahead of time. And just as important, to know exactly what to acquire and where to build. Our challenging is to optimize assets and capacity based on expected demand, manage increasingly scarce capital investment, reduce lead time to acquire resources, assets, and capacity, and position adequate assets and capacity in the right place at the right time to meet the expected demand. This is where operation research comes in. In today's talk, I walk you through a suite of OR tools to develop operating plan and manage assets and capacity. All the models have been developed in-house by the OR group at Norfolk Southern, unless noted otherwise. I'm going to cover 14 models in today's presentation. Of course, due to the time constraint, I'll stay at a high level, so you won't see a single mathematical equation. But I will stick around after presentation for questions. Now let's look at the diagram to the right. In the center is the operating plan. It's the foundation for asset and capacity management. There are 5 major asset categories: locomotive, rail car, train crew, rail yard, and track infrastructure. We'll go through each of these 5 components in detail in the following 2 sections. Developing operating plan. In this section, I'll talk about how Norfolk Southern uses OR models to develop a new operating plan and improve a current operating plan. From traffic to operating plan. Here is the workflow to develop a new operating plan. Starting with traffic data set, including historical shipments, new business, and future forecast. Next step is to develop blocking plan. A block is a group of rail cars going from one yard to the next yard. The railroad blocking problem is identical to the sorting problem facing US Postal Service. In the railroad context, mails are the rail cars, mailbags are blocks. The sorting process is called classification. Next step is to develop a train schedule. Train schedule includes train route, arrival, and departure time at each stop. A train carries one or more blocks. It picks up or sets out blocks along the route. Next is to optimize terminal clock. A terminal clock shows the inbound and outbound activities over 24 hours, and rail car connection from inbound to outbound trains. Last but not least is the network simulation. It simulates the new operating plan using the traffic dataset and generates volume reports and statistics for block, train, crew, terminal, and line density. Please note that a new operating plan may or may not go through every single step, depend on the scope and timeline. Developing blocking plan. The tool is called Optimal Blocking Model, or OBM. OBM generates an optimal blocking plan based on either historical or future traffic. In the map to the right, for illustration purpose, those are the blocks out of just 1 yard, considering that Norfolk Southern has hundreds of yards. So the blocking plan gets so complicated that it goes beyond manual process. The objective of OBM is to minimize car miles traveled and intermediate handling or classification. OBM can be used in several different ways. Zero-based plan for network redesign. Plan adjustments in one local area due to traffic shift, continuous improvement. OBM can also be used for sensitivity analysis. For example, what's the impact of increasing or decreasing blocking capacity at the yard? Last but not least, OBM can be used to optimize the entire network to better utilize the existing yard capacity. Moving on, designing train service. There are essentially two types of train service, scheduled and unscheduled. The scheduled train service is for manifest trains in the carload network, including general merchandise, automotive, and intermodal. The unscheduled train service to the right is primarily for unit train or bulk train, which is a dedicated service for bulk commodities such as coal, grain, crude oil, and so on. Designing scheduled train service, our tool is called Optimal Train Model, or OTM. OTM generates an optimal train schedule based on a given blocking plan. It determines train route, frequency, day of week operation, and detailed schedule or timetable. Also, OTM determines how blocks are moved by trains, that is, block train assignment, and where to pick up and set off each block. OTM minimizes train start, crew start, and car days. It is formulated as a combination of MIP and heuristics. Similarly, OTM can be used for zero-based plan like network redesign, incremental plan changes, or continuous improvement. Now move on to the unscheduled train service. Designing unscheduled train service, our tool is called unit train generator, or UTG. UTG is used to design unit train service. Unit train account for roughly 10% of total road trains. So it is important to plan these trains accurately. UTG can use either historical or future traffic as input. It uses statistical analysis to identify patterns in the unit train service. UTG generates complete train plan, including train symbol, route, schedule, frequency, and train size. Now move on to the next component in the operating plan, which is terminal clock. A terminal clock shows the activity in the yard over 24 hours. Let me turn on my pointer here. So the top half showing all the inbound trains. Okay, each bar is an inbound train, and the height of the bar is the size of the train. Also, you can see the two colors. The black is for loads, number of loads, and the white is for number of empties. The bottom half shows the outbound trains. So the terminal clock really divided into three shapes in different colors. We have one OR model to optimize terminal clock. The tool is called Terminal Clock Optimizer, of course, TCO. Terminal congestion is caused by multiple factors. For example, a car spends about 2/3 of its life at terminals. Bunching of inbound and outbound trains. They both causing resource contention, capacity shortage, and train delay. TCO is used to increase car velocity, which is a key element of PSR, or precision scheduled railroading, and reduce terminal congestion. TCO optimizes terminal clock by adjusting train arrivals and departures, subject to yard capacity constraints. So in this simple terminal clock, there are 3 trains coming into the yard between 1 p.m. and 2 p.m. So in this case, TCO will try to find how do I spread out these 3 trains, either advance some of the trains or push back some of the trains. So in that case, I can balance the inbound and outbound, balance the resources, but at the same time, minimize the car dwell time. The last step in developing a new operating plan is network simulation. Operating Plan Developer, or OPD, is a network simulator of virtual railroad. It simulates the entire Norfolk Southern operations and quantifies the impact of any changes. For example, you can shut down a yard and cut off a line in OPD to test the impact prior to implementation. OPD is a network planning and survey design tool, which has been heavily used at Norfolk Southern and in its transition to the precision scheduled railroading. It also used in yard rationalization. For example, Norfolk Southern recently downgraded Macon from a hump yard to a flat switching yard. Just as important, OPD is used for continuous improvement. That's all about operating plan. In the next section, I'll talk about how Norfolk Southern uses OR models to manage assets and capacity. Just to refresh your memory, let's revisit this diagram. I have already covered the centerpiece, that is operating plan. Now moving on to the 5 major assets: locomotive, rail car, train crew, rail yard, and track infrastructure. The first category is locomotive. We have 2 major applications for managing locomotives: locomotive fleet planning and real-time locomotive shop routing. So you will see a pattern here. For each asset, we normally have 2 different OR applications. One application is for planning, for strategic planning. Another application is for operations, for real-time optimization. First, locomotive fleet planning. Locomotive is expensive to own and maintain, so we don't want to have too many of them sitting around. On the other hand, lack of locomotives will cause train delay and hinder future growth. The fleet planning model is to determine the right fleet size. Second, real-time locomotive shop routing. Under FRA, Federal Railway Administration regulations, each locomotive has to go back to shop for inspection and maintenance after a fixed period, either 92 days or 184 days, depending on locomotive model. If a locomotive passes the FRA due date, it has to be shut down right there and towed to a shop. The real-time optimization model routes a FRA due locomotive to its home shop right before it's due. By doing so, we're able to reduce locomotive downtime, improve locomotive utilization, and operate the fleet effectively and efficiently. Now let's dive into the locomotive fleet planning. The OR tool is called Locomotive Assignment and Routing System, or LARS. LARS determines the locomotive fleet size to meet the traffic demand. Locomotive planning is a complex process involving many constraints and business rules. For example, train priority. In the model has higher priority than manifest and unit train. Special equipment, cab signal, locomotive speed limiter or LSL, for example. If a train is going through the Northeast corridor between Washington, D.C. and Boston, it's required that locomotive be equipped with the locomotive speed limiter or LSL. For algorithms, LARS uses approximation dynamic programming or ADP. It's a modeling framework combining optimization and simulation. Now, real-time locomotive shop routing. The same LARS model is used to optimize locomotive shop routing decisions to minimize locomotive downtime and maximize on-time arrivals. Model constraints. Each locomotive is assigned to a home shop for efficiency. Also, shop capacity is considered to reduce congestion. So far, from last year, the system was deployed last fall. So far, we have seen significant improvement in home shop compliance and on-time arrival. Given the success, the optimization system is being extended to optimize shop routing for unscheduled repairs. Now let's move on to the second asset category, railcars. Similar to locomotive, we have two major applications to manage railcars. The first is the strategic tool for railcar fleet planning. Just like locomotive, railcars are expensive to own and maintain. They're not available on a dealer's parking lot. So there's a long lead time between order and delivery. So it's important to determine the right fleet size in advance. The other application to the right is an optimization model for real-time empty car distribution, enabling Norfolk Southern to manage rail cars efficiently. After a rail car is unloaded and released, the model will determine the next load point by matching empty car with customer demand. The model optimizes supply demand and automates the car distribution process. Therefore, waybills are automatically generated from the model results. Now let's dive into the railcar fleet planning. Norfolk Southern railcar fleet has more than 50 different car types. Each car type has its own unique, specific set of customers and demand. Our model for railcar fleet planning is called Strategic Fleet Planning Model, SFPM. SFPM determines the optimal car supply plan to maximize profits for all the car types. It answers questions such as how much revenue will be earned, will not be earned if we choose to do nothing. Lease versus buy. Of course, this is the decision we are facing daily to lease a vehicle or not, or buy a vehicle. So same thing for Norfolk Southern. So which option is better? So in this case, the model actually looking at the demand to see if it's a sustainable demand over a long period of time. If we decide to buy, the model will recommend when to buy and how many to buy. SFPM has two key components. First is the Monte Carlo simulator, which generates a fleet outlook and quantify revenue or profit at risk if there's a shortage of car supply. The second component is an optimization model producing a 5-year schedule of car supply plan. Of course, including the normal decisions, buy, lease, repair, and modify. So in some cases, you may be a modify existing car type, surplus car type, and to fit a shortage car type. The second application is the real-time application. Our optimization system is embedded in an IT system, in an enterprise IT system called Teams. The optimizer is to maximize equipment utilization, minimize costs, and provide best customer service. Specifically, the model minimizes the rail car travel time and distance, reward on-time arrival, and providing the right equipment. Essentially, the model matches car supply with customer demand, formulated as a transportation problem and solved by CPLEX. For illustration purpose, let's see a hypothetical case, assuming 2 empty cars available, and there are 3 customer order cars. So the model just look at the supply and the demand, look different car types, the time traveled, and all this cost factor and rewards, and make the best decision and how to match, how to supply the 2 cars for the 3 customers. I would like to emphasize that the model not only optimizes the car distribution, but also automate the car distribution. I'll touch on that again at the end of the presentation. Next asset is train crew. We call the T&E crews. Again, there are 2 models for managing crews. The first model is for crew capacity planning. The model determines the right sizes of regular crew pool and actual boards. An actual board is a pool of workers who are available to cover for regular employees. The crew capacity planning model can be used to evaluate the impact of any changes in traffic volume, operating plan, rest rules, crew mark-off, and government regulations. To the right, the second model is for real-time crew optimization. Crew dispatching is a complex process which involves crew assignment and decision on deadhead and detention. Deadhead refers to crews moving between terminals without performing any work, without performing service. Detention refers to crews staying at a hotel at a away location. The model optimizes crew assignment and reposition to improve crew productivity and reduce crew-related costs. The real-time optimization model is currently under development and will be deployed in a year or so. So in today's presentation, I'll skip the detail at this time. Diving into the crew capacity planning tool. The business goal is to right-size regular pools and actual boards. The model objective function is to minimize train delay and subject to various constraints, such as hours of service, 6+2. It means 6 days of service followed by 2 days of rest. Max crew on duty time, minimum crew rest time, train schedule, crew profile. So there's many other constraints as well. So crew process is actually very complicated. The model is a combination of crew simulation and the pool size optimization. The output is the optimal size of each pool and actual board. Next asset, remember we have 5 assets. We talked about locomotive, rail car, and train crew. Now the 4th one, the yard capacity. The yard capacity planning tool is for both hump yard and flat switching yard. The business goal here is to better understand yard capacity to develop robust operating plan. Because it's not uncommon for people to overestimate or underestimate yard capacity. The model also allows us to evaluate the impact of changes in train plan, yard infrastructure, resources, and operating policy. The models are used to determine yard capacity in terms of daily throughput, number of blocks built, number of train built. The models can also optimize the allocation of yard resources. Since the model are developed based on key capacity drivers, such as the yard infrastructure, resources, operating plan, the model is very adaptive. We can adapt the model for different yards. Now come to the last asset, track infrastructure. LINEMAX is a planning tool to determine the capacity and utilization of a line segment. Line capacity is defined as the maximum number of trains that can operate on a line segment. LINEMAX takes into consideration of physical plant and traffic parameters, such as track authority, centralized traffic control, CTC, automated block signaling, ABS, and dark territory. Track type, either single track or double track. Siding information, siding length, number of sidings, and the distance between 2 consecutive sidings. Topography, grade and curvature. Operation, train speed, and headway separation. LINEMAX contains an integer programming model for dispatcher's meet and pass logic. Specifically, the model adds trains to fill available slots until all slots are filled, and like the train graph to the right. So once you reach that capacity, and that will be once you fill all the slots, and that will be the capacity for this line segment. To summarize, here's an overview of the tool I talked about in my presentation today. The x-axis represents different asset categories, while the y-axis represents the different levels of decision-making. The green boxes are the tools currently in production. The blue boxes are the tools currently being used, but will be extended to cover additional business needs. And the brown boxes are the tools currently under development. Some closing remarks. Starting with success factors. First, working closely with business partners. So optimization is not a black box. I mean, if they understand how a model works, they will be more likely to accept it and help you improve it. Second, aligning the model effort with company strategic plan and business needs. So when you work in the industry, it's all about here and now. What can you do me? What can you do for me now? So we have to deliver the models that are useful and help companies succeed. Next one, deliver an OR model as a software solution. And I think this is probably the most important point I want to get across. So once you deliver OR model as a software solution, it is always available. It's always going to work properly. And this is probably a pitfall I have seen in many OR shops in different industries. People develop fancy mathematical models, but the model are not ready or not working when people need it. Because like I said, when they need it today. They actually need it yesterday. Future trends. First is the real-time optimization systems. So real-time optimization brings about improvement in productivity and efficiency. People can actually see optimization in action. Automation. Automate decision-making and transform business process and culture. People have the tendency to override model recommendations for various reasons, but in some cases, it may lead to suboptimal. Last but not least, combining optimization with prediction for maximum benefits. That's one of the things we are thinking about doing next. For example, one case is look at the locomotive. So when we assign locomotive, can we look at locomotive reliability and consider the reliability as one of the factors for assignment? And because some of the trains has more sensitive service, and some of the trains have less sensitive service. So there's a differentiation of service level. And that's the end of my presentation. Any questions and comments?
Great. Thanks a lot, Clark, for this pretty comprehensive talk. You indeed show that you are doing work pretty much all over the railway ecosystem, which is really amazing to see. So we got quite some interesting questions. So maybe we could start with a few. One is about the performance of the models. So how do you measure effectiveness? Would be first part, and then the follow-up, how do you account for stochastic variables? So let's say for planning first, and then maybe you can say something about real time as well.
Okay, first question about performance. So the performance is really determined by the business needs. We talk about two different type of different type of models. One is for planning purpose, one for real time. So of course, the real time performance is much more stringent. Let's take the crew balancing model as example. And the crew balancing model, we can finish the model in 3 seconds. In the car distribution, we can finish each run in several minutes. It really depends on how quick you want to make decisions. So in some, like in planning, all the models we run is under 1 hour. But it probably take 30 minutes, in some cases take 20 minutes. But in that case, since people making decisions for long term, so they are not really constrained by the 1 hour, 2 hour kind of limitation. Okay, so to answer your questions, the performance is dictated by the business needs, and we'll model that accordingly. So second question is about randomness. You know, the fluctuation variation is a common factor. In some applications, we did take into consideration of randomness. One of the example I mentioned is SFPM, Strategic Fleet Planning Model. We use Monte Carlo simulation to estimate if we have a car shortage, how much revenue or profit will now be earned. So that's one. Also, another example is when we develop yard capacity model, we trying to put in some randomness in there just to simulate the variation, the daily variation in volume in arriving departure time. Hopefully I answered the question. But this is a good question, but it's kind of general question. It really depends on which model we're talking about and what is the need for that.
Okay, so there was one specific in this respect. How would you deal with unscheduled traffic, like unit trains in real time? Do you allocate them, or do you expect them somehow, or you just deal with them when they show up?
In the real time, of course, that's why it's called unscheduled. There's no schedule for them. But there's a system at Norfolk Southern. They do have something called a permit. So they do have a plan, either from the coal mine or from the grain elevator. They know the loading schedule. So they can plan according to the loading schedule at the origin. But that's you cannot really plan it long ahead of time. So it is more a real-time kind of planning.
Okay, thank you. And what about dealing with some bigger problems, like disruptions, or either weather-related, or strikes, or floods? So is that something that the models take care of? And would you be able to use the same models, or would you need to reach to different types? Could you say something there?
Great question. We do have one tool called Network Simulator. I talk about called OPD. So OPD, you can play what if in OPD to deal with any kind of weather issues, accidents, and things happening. So we use the network simulator to see, and if we have hurricane touchdown today, and what's our plan to deal with the hurricane? How we divert traffic away from the affected area. So that's, you can play what if. And in our plan, we want to develop, we don't have it yet. We want to have something called disruption management system. When you have disruption, just like airline. So when they have disruption, they can quickly recover from the disruption. So we want to have that system like that. So when we have disruption inside the system, how we change the train schedule and move crew around, and so we can recover from the disruption quickly. But we do have tool today to do the what if analysis. So if things happen, I can do this. If I do this, what happened? Okay. But it may not be optimal.
I see. Okay, good. Thank you. Well, we have Milan Janic with some questions, yes. If I got it right?
Yes. Thank you, Nicola, and thank you for a great presentation, which have been very, very substantive, but at a very general level, as you mentioned at the beginning. I learned in the US, when I was a guest for some time, about at Berkeley and MIT, the model is approximation of the reality. How these models because you haven't mentioned anything about assumption in your modeling, how these models are, let's say, deviate from the reality. That's one thing. And second is, do people who are going to implement the guidance from the models understand what they are supposed to do? I mean, people operating the system. And of course, have you tried implementing model and let's say assessing the benefits again from the model implementation in the segments, not in the whole system, but in the segments you have been implementing that? Have you been able to assess, for example, if the dwell time in the shunting yards have or the car turnaround time has let's say shortened, and the costs have been reduced, the staff has been optimized in terms of working shifts, numbers, structure, and so on and so on. And of course, I would like to just add about disruption management. Be aware that railways are less flexible than aviation in terms of disrupting management. I think you know that.
Milan, that's a very good point. Yes, one of the things, this is not related to a question. One of the things I explain to people is railroad is very constrained. We have single track. You can only run it on the ground. You know, in airline, you can fly different altitude. Like another exactly. A big difference between railroad and airline is airline reset every night. It doesn't matter if you have a really bad day. Tomorrow is a new day. And exactly. For us, we keep running 365 days. So when you have an issue, that issue you cannot reset. It keep have ripple effect, you know, for 2 weeks until. Actually,
you are the backbone of the transport system in the US. Railways are the backbone. That's for sure. I know.
So Milan, to go back to your 2 questions. So you have two pieces here. First about reality. Second about how to measure the performance. If I understand your question correctly there.
Yes, yes.
First of all, we have in my talk we have 2 sets of models. We have one set of model is optimization. Is for example linear programming, integer programming, mixed integer programming. This model there's going to be some limitations, some approximation built into it. On the other hand, we have the simulation model. So in the simulation model, we are able to build more real-world features into the simulation model. Of course, you know, simulation models have limitation because it cannot optimize. It can play what if. So to really answer your question is.
May I just please interrupt you at the beginning?
Yeah, no problem, please.
Just to mention something. Do you believe in optimum in this large system? Do you believe in optimums that the system can achieve optimum or not, or just near optimum?
So
models provide optimums, but can a real system reach the optimum suggested by the models? Regarding what Nicola also mentioned about disruptions, whether let's say some staff has not slept well, don't feel well, or whatever, not eager to work or something like that, you know?
I would say in most cases, even though we have approximation built into the model, the decision in general is much better than human decisions.
That's great. That's it.
It's a good decision. It may not be perfect decision. So that's how we explain to people, you know, just because model can see more things than people can see. Second, to answer your question about performance, like I mentioned in the presentation, some of the OR tools we have were heavily used by Norfolk Southern to achieve PSR, precision schedule railroading. I mean, that's a very hot topic in North America, not sure in Europe or in Asia. So we see a lot of improvement in terms of network performance, the car velocity, also the asset. So we actually reduced locomotive by several hundred. So, but the difficulty here is it's very hard to isolate the benefits of models, because model is helping people to make decisions. So you cannot say, hey, the velocity increased by 1 mile per hour. You cannot say this is because me. So because it's just hard to isolate. So that's kind of hard to really to quantify the benefits of models. But we do have one case I mentioned is the locomotive shop routing. Because it's a very controlled environment, we're actually seeing the improvement in the home shop compliance. Each FRW locomotive need to go to a home shop, because home shop is equipped with right people, right equipment. So they are more efficient to handle certain type of locomotives. So that's why you want to send locomotives to a home shop. So we saw the huge improvement in the home shop compliance. Also, we see the big increase in on-time arrival. Since, like I said, since it's very controlled environment, there's not other factors in there. We can say that's model make a big contribution here.
Okay, so great, thank you. I have another quick question, but then I invite everyone who is willing after 5 p.m. Clark is available for some more informal discussion, so feel free to stay longer. And yeah, if Clark, maybe you can say something about car distribution tool. Would it be active on all car types? And would you manage cars of all ownership types, or just railroad owned cars? And if that was too long, maybe you can stay with one of the questions.
I just write it down, the key points, so I don't forget it. So currently, the car distribution system handles the loose cars, and it doesn't handle intermodal cars. It doesn't optimize intermodal flight cars. It doesn't optimize the unit train cars, because a lot of cars like unit train, they're running like one set. So they load at origin, and they go to destination, the power plant, they unload it. The set will come back to the coal mine. So it's more like a shuttle. So there's really not opportunity, not a whole lot of opportunity to optimize. So the opportunity is really on these loose cars, the merchandise world. So that's first question. The second question is, I believe I have to go back and check. The car distribution system is only for railroad-owned cars, not for private car, because the private car are controlled by the customers.
Okay, that's clear. So I would like to close the formal part of the webinar. Really like to thank big time to Clark for a great presentation, and to all participants for your active involvement, and also to Sam from Tiger Analytics for giving the ideas about the work they are doing. So stay tuned. We'll continue in January next year, and who wants and is free to stay, Clark will be available for all the questions. So recording will be available, and we'll share the link and the slides afterwards. Thank you, everyone, and I wish you a great day.
Thank you, Nicola, for organizing this. Great job.
Thank you.